Next.js has one of the most impressive caching systems in modern frameworks, but as a beginner, it can feel overwhelming. In this video, I'll walk you through 4 core caching mechanisms in Next.js: the router cache, the full route cache, request memoization, and data cache. Each plays a different role in optimizing performance, and by the end, you'll know how and when to use each one. We'll kick off things with request memoization and build up from there, walking through each caching layer using visual and simple code examples. So let's take a look at request memoization. Here's a common situation. You got a route that includes a layout, a page, and several components, and some of them run functions like generate static params, generate metadata, or even their own data fetching. But what's common to all of them is they need the same data, so maybe request A, B, and C. Now, without memoization, each part of the tree would work independently and make the same fetch request, leading to a lot of duplicate calls. Request memoization solves this by making sure that only the first call for each unique request URL is actually sent. Every other identical request, no matter where it is in the React tree, reuses that first one. So instead of 15 calls for 3 pieces of data, you just make 3. This lets you fetch where you need to without worrying about duplication or prop drilling. So let's take a look at a visual representation of how a request memoization flow works. We start on the home route. This triggers a render, and somewhere in the tree, there is a fetch call to item 1. Before hitting the data source, the server first checks its memory request memoization layer. Since it's the first time the specific fetch has been called during this render, it results in a miss. There's nothing stored yet. So the request continues to the data cache or the external data source. It fetches the data and brings it back. Now, on the way back, it stores a promise in the in-memory memoization layer, not the actual data, but a reference to the ongoing or completed request. Now let's say there's another fetch call to the same URL that happens during the same render cycle. This time the server checks the memoization layer and finds a hit, so it reuses that promise instead of firing a new request. That's what you are seeing at the bottom right of the screen. Next.js is essentially saying, oh, I've already seen this request before, let me just reuse what I've got instead of doing it again. Now every repeated fetch for the same URL during this render will now share the same promise, whether it's still pending or already resolved. This keeps the render efficient, avoid duplicate network calls, and lets each component fetch what it needs without prop drilling or coordination. So in short, the first call triggers the request and stores it in the promise, and every identical call after that just reuses that promise. Now before we move on, let's quickly break down a few final bits about the request memoization. First, duration. This cache is short-lived. It only lasts during the server request while the React tree is rendering. When the render is done, it's gone. Second, revalidation isn't needed. Since the memoization is scoped into a single render, it doesn't persist across requests, it resets automatically, so there's nothing for you to manage. Now in terms of opting out, there's not much to worry about either. Memoization only applies to get fetch request. Anything like post, put, or delete isn't memoized anyway. And honestly, it's such a helpful optimization from React that you probably don't want to disable it. Also, a quick heads up, this is a React feature, not a Next.js one, but it still interacts with other Next.js cache mechanisms, which is why I have included it here. Now, it only applies inside React component tree, so fetches made in generate metadata, generate static params, layout, pages, or other server components will be memoized, but fetch route handlers won't be, since they're not a part of the React tree. So with that in mind, let's jump into a quick code example to wrap this up. Alright, so when you first open up the page.tsx in the home route, you'll notice something interesting. We're making quite a few API calls. Let's start by jumping into our help us file. This is where the fetch logic lives, and it's pretty simple. We're calling the Rick and Morty API, and we are measuring how long that call takes from start to finish using the performance.now. We are also logging out each step just to keep track of what's happening behind the scenes. Now, if we head back to our home route, you'll see that the generate metadata function is making the fetch call again. This time we are grabbing the data just to return the title and the description based on the first character. Ignore all the console logs for now, they're just there to help us to trace what's happening. They are for us, not for the user, and you wouldn't do that in a real app. Cool. Now, inside the home component, we make the same call twice, once on line 32 and once on line 38. Now don't worry, I know this isn't something you do in a normal app. This is just to show you what happens when you make multiple identical fetches inside the same component. Also, on line 55, we render the character summary component. And guess what? This also makes a fetch call. So to recap, there is one fetch call with generate metadata, 2 fetches from the home component, and 1 fetch call that happens in the character summary component. So that's 4 intended calls, all to the same API endpoint. Alright, now let's run the app and take a look at what happens in the browser. These are server-side calls, but thanks to the feature in Next.js, we are able to see the server console logs directly in the browser during development. So even though these are server logs, we can inspect them as we debug, which comes in super handy. Now, when we open the DevTools and check the consoles, you'll see logs for each intended fetch. They fetch from the homepage component, which is the first call and is a full network request. And then the fetch from the generate metadata function, which is also a fresh network call. These are the actual network requests. But then you'll notice that the subsequent calls for the homepage component, the second one that we spoke about, is much faster compared to the previous 2 calls. And then the one in the character summary is also extremely fast compared to the previous 2 calls. These are not new network requests. They are served directly from memory thanks to the request memoization. Next.js is smart enough to realize we're making the exact same fetch request with the same URL and the same options multiple times within a single server render pass. So rather than repeating the network request, it reuses the result from the first time that the specific request was resolved. That's why the second identical fetch in the home component and the fetch in the character summary are so much faster. They're not refetching from the network, they're pulling from the already fetched data in memory. Now, a quick side note, the reason the first 2 actual fetches from the home component and the initial generate metadata both have network latency isn't because we made too many calls, it's because Next.js can perform these fetches concurrently. It doesn't necessarily wait for one to finish before starting another if they're initiated close together in the rendering lifecycle. So both proceed in parallel, contributing to overall efficiency. So the key thing to understand here is that if you make the same fetch request multiple times during the same server render pass, Next.js will automatically deduplicate it for you. And you don't have to worry about redundant fetches slowing things down, they will get deduped. So this is request memoization in Next.js, subtle but extremely powerful. Now that we've seen how request memoization works during a single render, let's take it a step further. Let's break down how data caching works with a quick workflow example. Then we'll look at how you can revalidate this data manually and how to fine-tune the caching behavior with more precise control. We start by hitting a route, and in our case it's the home route. Inside the render cycle, we perform a fetch with the cache option set to force cache. This tells the server to cache the result and reuse it whenever possible. The first step is always in memory request memoization layer, and since it's the first call, that's a miss. Then the request checks the persistent data cache. Still a miss because it hasn't been cached yet, so it continues to the data source. It hits it and brings back the data. On the way back, it sets both the persistent cache, like a JSON blob, and the in-memory memoization on the promise. So on the next call, you'll hit both caches and skip the data source entirely. Now let's take a look at what happens when we set the option to no store. This one works differently. Again, it starts with the request memoization check, where it misses. Then, because we explicitly said no store, it skips the persistence data cache entirely. We go straight to the data source, hit it, bring it back to the results, and on the way back, we do not write anything to the persistent cache. But we do store the promise in memory for the current render cycle. That part stays the same. So to summarize this workflow quickly, when we use force cache, it tries all layers, stores it in both persistent and in memory. But when we use no store, it skips persistent cache entirely and only stores a memory promise for that render. This gives you fine-grained control over how data is cached and reused inside and across requests. Before moving on, there are a few more important things to note. First, in terms of duration, the data cache is persistent. It sticks around incoming requests and even across deployment unless you explicitly revalidate or opt out. When it comes to revalidation, we've got 2 main options. One is time-based revalidation, triggered by passing next.revalidate option with a time value. And the other one is on-demand revalidation using cache tags like revalidate tag or validating the path, which we'll walk through again in the code example. Lastly, if you want to skip caching altogether, you can also opt out by using the cache no store option in your fetch request. Now that we know exactly how it works, let's take a look at the flow of time-based revalidation and on-demand revalidations before exploring the code example. We start with the first uncached request where we pass the next revalidate option set to 60 seconds. This goes through the server and checks the persistent data cache. Since it's the first time the data is being fetched, we get a miss. So it continues to the data source, gets the data, then on the way back sets the response in the cache. Now the response is stored and ready to be reused for the next 60 seconds. Now if we make the same request again within 60 seconds, we hit the cache request. The response is served directly from the data cache, fast and efficient. No network call is needed. Once that 60-second window is passed, the data is marked as stale. So when a new request comes in, Next.js still serves the stale data immediately to keep things fast, but in the background it triggers a revalidation fetch to the data source. Once the fresh data returns, the cache is updated. Here, Next.js is using a stale-while-revalidate pattern, a concept borrowed from HTTP caching, which helps balance freshness and performance. The user gets a quick response and the app keeps its cache fresh behind the scenes. So to summarize, on the first request we get a miss, the data is fetched and cached. If we request the same data again within 60 seconds, we hit a cache and return the cache response. After 60 seconds, the data becomes stale. Next.js serves the stale response immediately, then revalidates it in the background and updates the cache data with fresh data. This gives us speed without sacrificing freshness. Now, time-based revalidation is great for data that does not need to be real-time, like content that rarely changes or isn't critical to update immediately. But what if you need to show users the most up-to-date data at the moment something changes? That's where on-demand revalidation comes in. So let's walk through how on-demand revalidation works in Next.js using cache tags. We'll start by tagging our fetch request. In our case, we'll use the letter A. And since it's the first time we're asking for this data, the server checks the persistent data cache and gets a miss. So it goes to the data source, fetches the data, and on the way back, it stores the response in the cache under the tag A and returns the result. Later on, something changes. Maybe a CMS update or a database write. We want to make sure that the next request gets a fresh data. This is what we call revalidate tag, and pass it the tag, which in our case A, which tells Next.js to purge anything that's cached with that tag, so the old data is now gone. Now when we make the same fetch again, we get another miss, since we just cleared the cache. So it hits the data source again, fetches the new data, stores it in a new cache under the tag A, and returns the response. This cycle of fetch, purge, and refetch gives you full control over when your data is updated. Now that we've covered both time-based and on-demand revalidation, let's walk through some simple code examples and see how these methods are implemented in practice. Let's take a quick overview on how the app structures before we dive into the caching behavior. Inside the data cache folder, you will find two key parts. One, a Next.js app, which is our front end, and the second folder is a server folder, which is Ono-powered API server, which returns the real-time data. Now the goal is to demonstrate different caching strategies using simple but real-time data source. This is why we've separated the backend so you can clearly see when the data updates and how caching is applied. To do that, I've created a lightweight server using Ono. It has a time route and that returns the current time and logs the request. This makes it easy to see when exactly the network request happened, and we also enable cores so our front end can access it. And we run the server locally on port 8080. Now, if we go to our main page in our front end, here we use a helper function called fetchTime from Ono API, which fetches the time from our server. When the page loads, we log the time returned from the API, and we display it alongside the time the page was rendered. This helps visualize what was cached and what's dynamic. Now let's jump into the helpers.ts file to check out how the fetch works. It fetches the current time from the Ono API and logs which component has made a call. I also included error handling so it gives us a clean and reusable function. Now if we return to the main page and if you scroll down a bit, you'll find two server actions. One is revalidate path, which revalidates a specific route, and two is the revalidate tag, which validates all the data tied to a tag. These are both from the cache module in Next.js and both enable on-demand revalidation of static data. I have also created two routes in this app. One is the API no-store route. This uses the no-store option, which tells Next.js to never cache the response and always fetch fresh data. And the second one is the API time-based, which uses revalidate to 10 seconds, which tells Next.js to cache the data for 10 seconds, then revalidate it in the background. We'll explore how both of these behave in the demo. Before we start, just make sure you run pnpm start on the server and then pnpm build and pnpm start on the front-end app to make sure it's all running. And then head into the localhost 3000 web page. Let's start by opening the main page. When we load it, we are using the force cache, which is the default caching behavior in Next.js. So even if the data changes behind the scenes, refreshing the page won't show as a new value. To revalidate a static page, we will need to use either the revalidate path or revalidate tag. This will trigger a revalidation on the server, and the next time we load the page, the data updates. So let's give it a go. And as you can see, the time has changed. And that's simply on-demand caching at work. Now let's head over to the API no-store route, where we've explicitly told Next.js not to cache the results at all. But now, as you can see, every time I refresh, it fetches fresh data. And finally, let's check out the API time-based route. This uses time-based revalidations, will be set to 10 seconds. If we refresh the page within that 10-second window, we get the cache data. But once that window passes, the next request triggers a background update and we will see a refreshed value. Now, just a note, when using time-based revalidation, the first request after a revalidation window expires will still serve stale data while triggering a background fetch. On the next request, the updated data will be shown. This is known as stale-while-revalidate, and I will link more information in the description below. And this wraps up the data cache demo. Once you get a feel for how these caching mode works, it becomes much easier to build flexible and high-performing apps with Next.js. And next, we will move into exploring full route cache. By default, Next.js caches rendered pages on the server. Not just the HTML, but also the React server component payload that helps React figure out how to hydrate and reconcile the page later. This cache lives in the route level and stores the full output of that route. So when it's hit, it's fast. So let's see what happens during the build. Let's say we are building the home route, and since it hasn't been cached yet, Next.js checks the full route cache and gets a miss. So it kicks off the rendering process. During this build-time rendering, it fetches any data needed, generates the React server component payload, which is basically structured instructions for how the page should be built, and renders the HTML. Once this is done, both the HTML and the payload are saved in the full route cache, ready to be reused. Now when a user actually visits that route, Next.js can skip all that work. It pulls everything, the HTML, the RSC payload, straight from the cache. Now on the client side, React instantly shows the HTML for that fast first paint. Then it uses the RSC payload to rebuild the componentry and figure out what needs hydration. Then the JavaScript kicks in and makes everything interactive. This is why full route caching is so powerful. It gives you speed and a smooth hydration experience. Now let's zoom out and look at how static and dynamic routes behave differently in this process. We'll walk through it step by step with a visual. So we start with a static route, like home. On the first visit, the client checks its in-memory route cache and it's a miss. Now, I know I haven't touched on this yet, but we'll cover this caching mechanism next. For now, just get a mental model that there is another caching mechanism on the client side that we'll come back to. Then it checks the server full route cache, and since it was pre-rendered during build, we get a hit. The server returns the cached HTML and the RSC payload, and the client stores that in memory for next time. Now take a dynamic route. The route to cache is a miss. Full route to cache is skipped since dynamic routes aren't built ahead of time. So Next.js renders that page on demand, fetches the data, builds the RSC payload, renders the HTML, and returns the result. The client stores it in the route to cache, but it's not persistent. It'll be gone on hard refresh or a new session. Now let's say the user navigates to one of these routes again. Both static and dynamic routes are now in the route to cache. So Next.js serves them instantly from memory, no need to hit the servers again. But the big difference is, static routes were ready from the build time, already cached and optimized. Dynamic routes had to be generated on demand first, then stored in a temporary memory. That's why sometimes you notice a little delay the first time you hit a dynamic page, but after that it's quick. So in short, static is pre-rendered at build, persistent in full cache route. Dynamic is rendered on request and cached only in that memory for that session. Okay, now let's bring in the last piece before the code example. How long does this cache last and how can it be invalidated? The full route cache is persistent by default, which means the rendered HTML and the RSC payload are used across all users' requests, unless something triggers an invalidation. There are two main ways which this cache can be invalidated. First is the revalidating the data cache. When you revalidate data using methods we've already covered, like time-based or on-demand revalidation, it will also trigger a fresh render of that page. That new render output replaces what was previously stored in the full router cache. The second way is redeploying your app. Unlike data cache, which can persist across deployments, the full route cache is always cleared on a new deploy. You can also opt out of the full route cache altogether. This means the route is rendered fresh on every request. There are a few ways to do that. First is using the dynamic API, which we'll cover in the code example next. And the second is using uncached fetch, which is the no store we covered before. Now that we understand how the full route cache works and what the options are, let's take a look at a code example and see it in action. Make sure you navigate to the full route cache folder and open the main page. Now this is a basic homepage. There's not much going on here visually, but the key thing here is to know that the page is making a fetch call with a function called getData, which lives in our helpers.ts file. Now if we go into the helpers.ts file, inside this file you will see that we're making a standard fetch to the Rick and Morty API. And all we're doing is logging the start and end time of the request. So we are tracking how long it takes. Now if you go back to the main page, you'll also notice a bunch of commented out config options. Let's ignore this for now, we will come back to this later. For now, let's run the web app by running pnpm build and pnpm start. Now once the build is finished, we can scroll down slightly and look at the output for the route. You'll see that it has a circle next to it. This means the page was built as a static route and using the full route cache. Now let's take a look at the browser and the home page. Now if you look at the home page, even if I refresh the page, nothing is going to happen. We're not going to make those calls again because Next.js isn't running the fetch, it's serving the static build version. If we want to refetch it, we would have to make the page dynamic. Now it's worth noting that there's nothing wrong with the static pages. In fact, they are more performant because they load quicker. But for many cases like real-time or frequently updated data, you'd want to make the page dynamic. There are a few ways of doing that and we'll go through them quickly. One is the route segment config. We can use export const dynamic and set it to force dynamic to opt out of the full route cache and treat the route as fully dynamic. Or we can set export const revalidate to 0, which uses incremental static regeneration but with 0-second revalidation, effectively dynamic. The second method is using dynamic APIs, such as cookies or headers, and we can use them inside a component and it will automatically make the route dynamic. And lastly, we can also change the fetch options, which we've already done before, to cache no store, or we can pass in the revalidate to 0 to revalidate it on every request. All these methods effectively opt out of the full route cache and make the route dynamic. I would highly recommend checking the official Next.js documentation to see the full list of caching behaviors and how they impact rendering. So for now, let's try one of these in action. Let's leave the force dynamic uncommented and comment out the rest, and then run pnpm build and pnpm start and wait for it to finish. Once the server is running, if you scroll down and you look at the routes again, you should now see a dynamic lambda symbol in the terminal. When you refresh the home page now, you'll notice fresh log appear every time. That's because the server is rerunning the fetch on each request. The route is now dynamic. And that's it for the full route cache demo. Next, let's take a look at the client-side router cache. In the previous section, we explored how the full router cache works on the server, and as a part of that, we also route the cache in action. Now let's bring that diagram back into focus, especially the ping box on the client labeled router cache. This is the final caching mechanism we're breaking down, the client-side cache that lives in our browser. This cache is specific to Next.js and its server component architecture. It stores segments of React server components payload, layouts, loading states, and sometimes pages. If you look at the home route and trace the arrows of the miss and set boxes under the route cache, you'll see that the first visit always results in a miss. That's expected behavior as it's the very first time Next.js sees that route. But once it's fetched, it gets stored locally. From then on, whenever a user navigates through your app, the router segments are served instantly from the router cache. This is where client-side speed boost really kicks in. Fast transition, no flickers, no reloads. By default, layouts and loading states are always cached and reused. Pages, however, aren't cached unless you opt in the experimental stale times config. But even without explicit caching, pages are still reused on browser back and forward navigation. Let's break this down further, just like we did with the other caching layers. Let's talk about duration first. The router cache lives in your browser's temporary memory. It sticks around for as long as the session is active, meaning it's cleared on the full page refresh and as long as each segment remains fresh. So we default prefetching when prefetch is equal to null or is completely left out. Static segments will last 5 minutes while dynamic ones aren't cached at all. With full prefetching, where you set prefetch to equals true or router.prefetch, both static and dynamic route are cached for 5 minutes. Each segment starts its own freshness timer at the moment it's prefetched. You can control this duration with the experimental stale times config. Now let's move into invalidation. You can invalidate a router's cache in 3 main ways. Use the revalidate path or revalidate tag in the server actions, which we've covered earlier. Set or delete cookies, very useful for authentication or sensitive routes. Or we can simply call router.refresh to refetch the current route from the server. And finally, to opt out, as of Next.js, page segments are opted out by default. If you don't want to prefetch at all, then you can set the prefetch to false on the link component. So to sum it up quickly, this cache kicks in after the first visit, boosts speed by caching route segments like layouts and loading states, and works quietly behind the scenes to make navigations feel smoother. Alright, now that we understand how this works, let's close this section with a quick code example. Starting on the home page, this is a simple landing view with a link to the about page. The about page itself is just a basic placeholder, nothing fancy, just plain text. The main thing to look at is the link on the home page that navigates to the about page. Right now it's set to prefetch equals false, so we can see exactly how the router behaves without preloading. We'll walk through how that changes things in a moment. To run this in production and see the real behavior, let's run pnpm build and pnpm start. As we go through this, first we'll see what happens when prefetching is off. After a hard refresh, we are not making any network requests to the about page until I click the link. Now that I click it, you'll see a network request has been fired. That's the app fetching the route on demand. If I go back to the home page and then click to go back to the about page again, you'll see no new network requests are fired. This is router cache at work. The rendered page is in memory and reused instantly. Next, let's remove the prefetch equals false and go back to the default behavior, which allows Next.js to prefetch it automatically. Let's run the build and start the app again, and then refresh the browser, and let's see what change that made. Now, when I refresh the browser, even though I'm still on the home page, you will already see the request to the server for the about page. That's prefetching in action. To inspect this, go to the network tab and then find the about page request. Click on it, and under the headers tab, you will see an important line. The next router prefetch is set to 1. That shows that Next.js is doing the work in the background before we even click. When I now click the link, there is no network request. The prefetch data is reused. Then we go back, click it again, still no network request. The router cache takes over from here and keeps the rendered page in memory. And this is it for this video. I hope you really enjoyed this deep dive into Next.js and the caching mechanisms. If you like this video, please make sure you click like, subscribe and share it. It helps a lot. This video took a long time to make and I hope it was worth your while. I hope you learned something from it, and until next time, take care.